when we actually put something into storage, or when we get something out of storage. Or second, noise can also happen over time. So I already stored something, but you can think of this bit, which is stored on your hard drive, passing through a noisy channel just because time passes. And these errors can happen. Okay. So now I want to send not just one bit, but many bits. So if I send many bits and I have the identity channel, all is great. Out comes what I put in. If I actually input the bits here, but I have a bit flip channel here, then the transmission is unreliable. So sometimes what comes out is not actually what we put in. I mean, I guess you're all familiar with this. And in fact, clearly you can make transmission reliable. What's something that you're all intuitively familiar with? Namely, we can use error correction. So suppose we have many bits, m bits. We could encode it somehow. We'll send it through all these channels that we have available. And afterwards, we do some decoding, where we correct the errors that have happened. So I wanted to introduce two important quantities, namely, that depend on namely how many bits we put in here and how many channels we have. So say we have m bits, and we have some number of channels, so some number of, say, storage bits. And let's say, for example, that we have many input bits, 1,000, and I have only one channel. So you can think of, I can only store one bit, and that one may be also a bit noisy. So do you expect this to work? I guess probably not. And so it depends on what is called the rate, namely the number of bits that we want to send per channel use. So here's the number of bits m and the number of channels n. And the point I want to make here is that error correction schemes cannot be arbitrarily good, as you probably expect. So this here is the rate, and with every channel there's something called the capacity, and it has the following property. If we try to send not too many bits per channel use, so the rate is smaller than this number called the capacity, then we can transmit reliably, so what goes out is exactly what comes in. But if the rate is greater than the capacity, then in fact there exists no error correction scheme, so there's nothing you could possibly do such that you get exactly out what you put in. So there are some limitations inherent in this problem, and your error correction schemes cannot be arbitrarily good. And in fact, it gets even worse. Namely, as you are above capacity, so if you try to send too many bits, then your chance of reconstruction, so that your probability that in fact you'll manage to get out exactly what comes in, goes to 0 if you try to send very many bits and the number of channels is large. So I guess the point I want to make here is that given only a certain number of noisy storage bits, we cannot send arbitrarily many bits. I guess that's intuitive. And in fact, the important thing is that not only can we not send in arbitrarily many bits, our chance of really getting out exactly what we put in is negligible. Okay. Now one can show, in fact, we have shown that the same holds for a large class of quantum channels. I don't want to talk about this, but the intuition is the same here. If the rate is above the capacity, we are in really bad shape. Okay. So I can now explain to you exactly what the assumption is we're going to make. So if a party is cheating, we allow him to be computationally all-powerful. Maybe in the basement he has a quantum computer, he can perform all error correction, he can break RSA, he has an unlimited amount of classical storage. All his actions happen sort of instantaneous, any encoding procedure, so there's no storage involved there. However, he does have noisy quantum storage. So what we will do is in the protocol, there will be certain waiting times. Say we wait for 2 milliseconds. at which point the noise accumulates in storage. And so what the adversary can do, so here he has some information, maybe he has some qubits, maybe some classical bits. He can measure them, whatever he wants. Like I said, he may have a quantum computer. So he can store as much classical information as he wants. But his quantum information has to use this noisy storage. So he has some number of these noisy storage channels. And I will tell you later what this number means. And he can perform an arbitrary encoding, whatever he wants. Okay, so this is what we're going to assume. Now, as I said, we're going to actually use quantum to achieve this. And so I want to talk a little bit about what are quantum bits, and in particular, what are uncertainty relations. So, I mean, maybe some of you have come to Vadim's talk yesterday, and one possible way to encode a classical bit into what's called a qubit, a quantum bit, is that we encode it into the state of some photon. So say we choose a particular encoding, and it has the property that if we measure it, knowing the encoding, we get out exactly what we put in. You say, this is not very exciting. But unlike in classical bits, there exist more than one ways to do such an encoding into a photon. And some of these different encodings have very interesting properties. So I will just tell you what the properties are. So I will use a blue encoding and a red encoding. So for example, these are different polarization directions of the photon. And all of them have the property that if I say choose the red encoding, and I perform the red measurement, then I get out exactly what I put in. Okay. Now, let me say a bit about what the peculiar properties of these quantum bits are. So unlike in classical bits, we cannot just copy them. It's going to be very important. And these two encodings actually also have some quite funny properties. So we can choose, for example, a blue encoding and a red encoding. They're such that, say, I've chosen the blue encoding here, but now I perform a measurement assuming the red encoding, and I don't get back what I put in, but with some probability half I get a 0, and with some probability half I get the 1. We can also turn this around, of course. So say I've actually chosen the red encoding, but now I'm going to measure assuming the blue encoding, and again I get with probability half 0, and with probability half I get a 1. Okay. Well, I guess I can hold the microphone. That's maybe okay. Okay, thanks. So maybe to say now, for the people who can actually understand me, I wasn't aware. So if I choose the red encoding, but I make a measurement assuming the blue one, I don't get out what I put in, but I get with probability half a 0 and with probability half a 1. Okay. So to explain uncertainty relations, let's imagine we're going to play the following game. I'm going to choose a bit with probability half. So I flip a coin, and I get either a 0 or 1. And I do the same thing again. So I will flip a coin, and I will choose either the blue or the red encoding. And I challenge Bob to guess my bit. So say I've chosen bit 0, and maybe I've chosen the blue encoding. So I send it to Bob, and Bob can do anything that he wants. Maybe he has a quantum computer, I'm not sure what he does. But whatever he does, so he'll output some classical bit, but the probability that